I trust everybody's rested from their quiet evening, ready to do some work. Many years ago, I was invited to do a talk at a NATO workshop in Greece, and I was standing at the back of the room beside Brian Gardner, sort of an art survey. And he leaned over and whispered in my ear that why is it that these other instruments that are kept in thermally controlled enclosures have poor wavelength stability compared to Brewer, when the Brewer isn't even temperature controlled at all? And so I tried to explain to them some of the things I'm going to talk about today, the elements of design that go into the instrument that lead to its behavior and lead to its stability. This is kind of a long and tangled tale of the origin of the Brewer. David Wardle was a student at Cambridge doing his PhD in the early 60s, and he designed a spectrometer with a grating that had two photomultipliers to measure two different wavelengths. It was very sensitive, large aperture, collected a lot of light, because he went off to Resolute Bay in northern Canada to make measurements of ozone through the polar night on stars. When he finished his PhD, he went to work as a lecturer at the University of Toronto, working with Alan Brewer, and did the initial design work for the spectrometer. Alan had realized that this was quite an advance to start using a diffraction grating with higher resolution and lower scale light, and decided that it was time to design an instrument to measure ozone. Well, David did sort of the back of the envelope calculation and pretty quickly came to the conclusion that you couldn't measure ozone with a single monochromator because of the X-ray light issue. Light of the wrong wavelength contaminating the short wavelength because of the huge gradient in intensity through the region 310 to 225 when there's a lot of ozone in the patch. And so he designed a double monochromator using gradients. This is a scan of the original drawing that he did of the instrument. You can see there's one continuous mount here that carries two gratings, and one half of the instrument disperses the light, and then there were prisms mounted that would pass the beam through the plate to the other side, and then it would go backwards through an identical monochromator to the final exit slip. The problem we had with the instrument after David had left and we were trying to finish it off was that it was practically impossible to align the thing and have it stay in alignment as you move the grating, because it means that not only do the optics have to be identical in the two halves of the instrument, you actually have to align the two halves of the instrument just perfectly, or you have trouble with throughput with the sensitivity of the instrument. One of the novel features of the instrument was the use of little piezoelectric vanes that could open and close the individual slips very rapidly. Unfortunately, at a certain point we were unable to buy that material anymore, and that's when the instrument design was changed over to use stepping motors. So anyway, the demise of the instrument was the decision to turn it into a single monochromator, and we cut it in half and built two instruments, and one of them wound up measuring ozone, and the other one wound up measuring NO2. So I'm going to talk a little bit about the detail of the instrument. It becomes kind of a repetitive story to a certain extent once we get through a couple of examples. Basically, there's a very careful optical design of the instrument, but the important thing in making sure that the instrument will be stable in the long term is to handle the mechanical design issues very carefully. You have to make sure that you carry loads in tension or compression so that you get the maximum value of the strength of the material. Bending is a very difficult thing to do because it means you need very, very heavy material, and then the weight of the material itself becomes a problem in terms of the loads. You have to have a clear understanding of how the system is integrated, and you have to provide temperature compensation if there design, the basic underlying principle is that a solid body has 6 degrees of freedom. There's 3 directions of translation, and there are 3 axes of rotation. And if you're going to constrain something so that it stays in the same place, you have to control all 3 degrees of freedom. But if you over-constrain them, then you wind up with the position of an object being a balance of forces acting on the body, bending it, essentially. And that means that if anything changes in the system, like the temperature or the load or the orientation of the system, you'll find that things move around. And even can cause things to break when temperature changes. One visible external example of the use of kinematic mount is the actual mounting screws that allow you to adjust the tilt of the brewer in connecting it to the tracker. There are essentially 3 points where the screws coming out of the tracker touch the brewer, and that means that you can take the brewer on and off and maintain perfect alignment of the optics relative to the tracker axis. And the way that works is like this. There are two different methods for achieving a kinematic mount. This is one. It's the one I prefer. If you think about having 3 ball-end mounts here, 3 ball-end screws, if you put one ball into a cone, then it's going to locate that cone exactly and control the degrees of translation. Once you've pushed it down onto that ball, that completely determines the physical location of that point on the instrument or the box that you're trying to place. If we have another mount here, which is sort of a wedge shape that the ball can go into, then it doesn't try to control the spacing between the two because it's a wedge, but it completely constrains the rotation of the instrument about the other mount. That controls all but 1 degree of freedom, and the last degree of freedom is just pushing a plane surface down on top of the ball. So you can just take this object, drop it onto those 3 mounts, and it will be completely constrained identically every time because the sphere can only fit into the cone in one location. These principles are used inside the instrument. The diffraction grating mount is one example. I'll show the detail of the mount. While I'm here, though, I'm going to talk a little bit about the way the rotation of the grating is controlled. If you mount anything on a conventional bearing, like a ball bearing or a sleeve bearing, then there's a combination of issues that show up. One is the difference between static friction and dynamic friction. In other words, you have to push something quite hard to break the static friction. And once it's broken, then it can move more easily. So what happens is, if you're going to try and make an infinitesimal rotation, and you're doing it by having a long lever arm that operates a mount on bearings, what happens is you have to push on the arm until the arm distorts enough to produce the force needed to overcome the friction. And then once you overcome the static friction, then the arm will relax elastically, and you'll have a small rotation that was unintended. And what this causes is hysteresis. As you start to move forward, the thing will not move for a while, and then it'll jump to a new position and then continue to move relatively smoothly if you keep going. But if you turn around and start to go back, the same thing happens. You have to get force on the thing to bend the arm enough to overcome static friction. So you wind up with a system that has very nasty behavior in terms of trying to plot wavelength against position. So in the brewer, we actually use a cross-spring mount. There's a steel wire here and another one there. And there's an identical mount on the bottom of the grating. So that actually controls all the degrees of freedom except the vertical motion and the rotation. In order to control the vertical motion, there's a vertical wire that goes down from the fixed point here down to the top of the grating mount. and that keeps the grating mount from being able to translate up and down on the springs. So that leaves only the rotational degree of freedom, which is controlled by the motion of the stepper motor driving the micrometer. So the point is that there's a balance of forces here so that there is no actual friction. If you push on the arm, it will move, and there will be no hysteresis in the motion. It's also very good from the standpoint of temperature because it'll work properly at all temperatures. A conventional bearing with lubricant in it, if it gets cold, it's not going to work the same as it does when it's warm. The three-point mount is also used on the back of the grating in order to be able to control the degrees of freedom. There's a hole, a slot, and a plane, the same as I showed in the other picture. These two screws are used to control the rotation of the grating about an axis through its center, and that allows us to make sure that the lines are aligned vertically so that the spectrum image is as sharply focused as possible. And the only other degree of freedom we need is the ability to tilt the thing in and out. We don't need to be able to rotate it because the grating arm allows us to rotate the grating. And so if it's just approximately in the right place, we can control the rotational angle with the grating arm and be able to position any wavelength that we want along the focal plane. But we need to have the tilt here so that we can adjust the alignment to have the rays traveling parallel to the base plate through the instrument. Another spot in the instrument where kinematic mount is made is the positioning of the mirror. There are actually three ball end screws on the mirror. If you have 3 points, it completely constrains a spherical surface. So as long as the mirror is pushed in against the three screws, it will be in exactly the same place every time. You can remove it and then put it back in, and it will be in precisely the same place because it has no choice but to have those 3 points to define the sphere. And here's a good close-up of the drive motor for the micrometer. The precision with which this is working is on the order of wavelengths of light at the grating arm, and of course a very, very tiny angle corresponding to that small motion. Here's a schematic of the mirror mount. There are 3 different points and a spherical surface, and the springs merely locate the surface up against the 3 points that define the location of that sphere in space. And of course, the surface of the mirror is finished to wavelengths of light, so this is a very precise positioning of the optical surfaces. Some practical things when handling optics. Don't touch any of those surfaces with your hands. They're all front surface aluminized coatings, and it will damage them. It's very difficult to wash them. It's a good idea to wear some kind of gloves when you're handling the optics, just to make sure that you don't accidentally touch something and leave material from your fingers on you. But the most important thing to realize is that the surfaces always look much worse than they actually are because you're seeing scattered light against a dark background. And it's almost always better to leave things alone than to try and wash them. It's very tricky to wash front surface optics. The surfaces really need to be a virtual write-off before it's worth trying to clean them. And of course, you have to know how to do it properly. Now, the stability of the wavelength in the instrument is related to a number of things, the individual optical components. There's the position and rotation of the correction lens just behind the entrance slit. This is sometimes overlooked because it seems like it shouldn't matter very much. But in fact, because it's a lens that has both a spherical component and a cylindrical component, there is an orientation to it, and that affects the resolution in the imaging at the focal point. Obviously, the rotation of the main mirror in both axes is important in terms of having the optics aligned symmetrically, and in terms of the tilt in the other direction, in order to make the principal ray run along the axis of the instrument parallel to the base plate. Grading orientation, of course, is important. I already mentioned the issue of the requirement of getting the grading lines vertical in order to achieve the best image at the focal plane. And there's also the question of the vertical alignment of the spectral image. When the instrument is properly aligned, the spectrum on the exit slits will be completely parallel to the base plate. And when it's properly aligned in the vertical, it should be centered. The exit slits are deliberately made about 50% longer than the image of the entrance slit, so that if you have minor misalignments in the vertical, you still collect all of the light, and it doesn't affect the result. Clearly, if the thing is out of alignment and the spectrum is tilted a little bit, and it gets near the edge of the slit, then one wavelength will be affected more than the others, and this will make a change in the ability to measure ozone properly. We also have the order filter in the instrument. In the Mark IIs and Mark IVs, we have the nickel sulfate and cobalt glass, and they are very susceptible to damage by moisture. So it's very important that they stay properly located, because if there's any gradient across the filter and the filter moves, it can act differently on different wavelengths, because different slits go through different parts of the filter. Again, just a quick look at the Brewer. The issues for alignment are basically first getting the tilt of this mirror correct, so that the incoming beam, the collimated beam striking the grating, arrives in the center of the grating. And having done that, then the tilt of the grating has to be adjusted so that the outgoing beam winds up in the right place on the mirror. And at that point, you can do a focus test on the instrument and adjust the screws in and out in order to bring the spectrum into focus at the focal plane. We actually have an algorithm for doing that by transporting a line source across the instrument field of view. You can actually use the micrometer to measure the location of the image of the entrance slit. There's a picture with some diagrammatic lines on it, so you can understand the layout. There's the top and bottom cross springs, the vertical torsion member that keeps the grating in the right position in the vertical, and of course another set of springs at the bottom. I've outlined the grating arm here, and that's acted on by the micrometer through a push rod here. Now you can see this is like 15 centimeters long, so motions on the order of a 100th of a millimeter are actually a very, very small angular displacement on the grating. And you can see the constraint for the mirror is a leaf spring here, and another one up here that simply pushes the grating against the three screws. There's enough room in here that the grating is not trapped, or not the grating, the mirror is not trapped, so that the springs can push up against the screws. And the springs have something like a couple of G's on them, so that the mirror will stay properly oriented even if you turn the instrument upside down. Line position measurements can be made to a fraction of a step by interpolating from measurements made at sequential step positions. In fact, the measurement can be made to a fraction of a step even if the measurement of a line is made in 10-step intervals. So the signal to noise plus the stability of the instrument allows a very, very accurate positioning of the lines, which is important because a shift in wavelength will actually produce a change in the apparent amount of ozone. This is a picture from the side of the double brewer. The interesting thing with the double brewer, in order to avoid the alignment issues that we had and the design problems of the original double that David Wardle had made, and to make it easy to put the instrument together, The double brewer is actually more or less two single brewers coupled together with mirrors on the, at the position where the normal exit slits would be. The idea behind this is that by using separate controls on the two instruments, we can actually mathematically force the instrument to be in alignment. So as you take a scan, you can have a dispersion relation that connects one instrument to the other, and as you move the micrometer that operates in the dispersing instrument, you can move the one in the recombining instrument to maintain complete overlap between the slit images in the two instruments. So if they have slightly different dispersion, you can actually correct it mathematically in the operation of the instrument. In order to find out what the relationship is between the two instruments, we use white light from the standard lamp and find out what step number in the dispersing instrument matches up with what step number in the recombining instrument. And then that relationship is stored away and used whenever a scan needs to be made. One of the issues that we're still having a little trouble with is the temperature coefficient of the instrument. It does change its wavelengths by a few steps over 20 or 30 degrees C, and we've been working on compensation. In the original design, we assumed that each instrument would have the same temperature coefficient and that we could actually correct it by putting the right materials in the push rod so that as the instrument grows with temperature, the aluminum gets longer, and the wavelength shift, we could compensate for that wavelength shift with the temperature coefficient of the push rod. But unfortunately, it seems that the instruments are sufficiently different that we can't just use one push rod combination for all instruments. So we're still trying to work on that a little bit. It's not a very big problem because the instrument automatically recalibrates its wavelengths on a mercury line, but it would mean that we could do fewer calibrations, which would be healthier for the instrument in the long run.